All right, in this part, which is going to be very brief, I'm going to show you, now that you have seen a little bit about how curved arrows work, I'm going to show you how you can make a prediction of what reaction might happen between two molecules using what you already know. Um, so that's the focus today. Um, remember from the first lecture, we have three different moves we can make with curved arrows. Um, Number one, we can show a lone pair getting shared with a new atom. In other words, form a new bond. We can show a bonding pair becoming a lone pair. In other words, break a bond. Or we have those cases where a bond moves uh, from between two atoms to between one of those atoms and a new atom. So break and form at the same time. So everything's going to happen using just those three kinds of moves. Um, so if you want to make a prediction about what might happen, you already have a tool to do this. Um, Back in Module 2, you talked about polarity of molecules, and you saw that we can identify where we have partial positive and partial negative charges within a molecule. Um, so take a moment, assign partial positive and negative charges to these two molecules. Hopefully, what you came up with is nitrogen has a higher electronegativity than hydrogen. So nitrogen is going to be partially negative. Hydrogen is going to be partially positive. Same thing in this other molecule. Oxygen has a higher electronegativity than hydrogen, so it's going to be partially negative. Hydrogen is going to be partially positive. All right. So you start with polarity, and then think about our three moves. A lone pair getting shared with a new atom. Well, generally, uh, a lone pair is where we have a concentration of electrons, right? Um, so when we do this, we want to share from partially negative toward something that's partially positive, right? When you think about two molecules approaching each other, negative part of one is going to be attracted to the positive part of another. If the two molecules take that to the extreme, then that partially negative atom can share a lone pair with the new atom. So it's sort of just this polarity attraction, this dipole-dipole attraction, as you might have called it in your first chemistry class, really being taken to the extreme, where the two molecules are not just like, hey, let's have positive and negative hang out near each other. Let's take that relationship to the next level and form a new bond. Um, so when I think about these two molecules, I'm going to ask myself what parts will be attracted to each other. And for these, there's really two options. Um, I could imagine the nitrogen being attracted to one of the hydrogens of water, right? Opposites attract. Um, or I could imagine the oxygen being attracted to one of the hydrogens of NH3, also known as ammonia. Um, so I'm going to identify those two possibilities, and then I'm going to think about, okay, what would it look like if we took one of those attractions to the extreme and we donated electrons or shared electrons from negative to positive? So let's use curved arrows to do that. So let's share electrons from a partial negative to a partial positive. You can decide which one you want to do first. I'm going to start with the pink one. So in this pink one, I chose the nitrogen partial negative sharing with the hydrogen partial positive. Well, when I want to show sharing of a lone pair, I'm going to start my arrow at the lone pair, right? From negative. So this is start of the arrow. To positive. So this is going to be the end of the arrow. So I would draw an arrow from this lone pair to the hydrogen. Remember, arrows always have to start at a pair of electrons, and they're going to end at an atom. Now, the second part tells me if I need to break a bond, I may need to break a bond to make space. Hydrogen, I know, can only make one bond. So I can't just make a new bond to hydrogen. If I'm going to make a new bond to hydrogen, I need to break a bond to make space. In other words, these two electrons that are on hydrogen that are shared between hydrogen and oxygen here, I'll highlight them in green, they're going to have to go away from hydrogen. So I'm going to break that bond and leave it to the oxygen. So what will that give me? Now my nitrogen would be bonded to 4 hydrogen atoms. My oxygen is only bonded to 1 hydrogen atom, and it now has 3 lone pairs. Hopefully you're skilled enough with formal charges that you can quickly recognize, well, my nitrogen now is going to have a positive formal charge. My oxygen is going to have a negative formal charge. So that is one potential reaction that could happen between these two. Sharing from negative to positive, breaking a bond to make space. I also identified another potential interaction, this one in blue. So I've done the one in pink. Let's now do the one in blue. So that would be where I'm going to share from the negative charge on the partial negative on oxygen to the partial positive on hydrogen in the other molecule. So again, I'm going to start my arrow at the partial negative atom, and I'm going to end my arrow at the partial positive atom. And again, I'm going to need to break a bond to make space. You can pretty much ignore the fact that I drew this in this trigonal pyramid geometry. I didn't really need to include the wedge and dash bonds here. Sometimes I just get in the habit of drawing things in that correct geometry. You could have left those as flat lines and that would be fine. So I'm going to share from negative to positive. I break a bond to make space. And what will that give me? Nitrogen now has 2 lone pairs. It's bonded to 2 hydrogens still. Oxygen now only has 1 lone pair, and it's bonded to 3 hydrogens. And again, hopefully you recognize relatively quickly, nitrogen now has extra electrons. So it's got a negative formal charge. Oxygen is down an electron, so it's got a positive formal charge. So again, we shared from negative to positive. We broke a bond to make space. And we came up with 2 possibilities. So just for these 2 molecules, we came up with 2 simple predictions of what might happen when they get together. And this is really useful as a tool when you start to think about how reactions might happen. And the question of which of these 2 is more likely to happen, we'll address in a moment. And for this particular kind of reaction where you're forming and breaking bonds to a partially positive hydrogen, Module 12 is all about this kind of reaction. So you learn some more predictive tools there. But even as a first pass, just knowing what you know from Module 2, you could predict these two possibilities. So now let's talk about which one is more likely. So I look at my two pathways that I considered, and I want to look at the two sets of products. So I'm comparing these products to these products. And I have those simple rules for stability that I've been using since Module 1. I look and say both of them follow the octet rule. So that's the first thing I evaluate is the octet rule. So both sets of products follow the octet rule. Because each atom has 4 pairs of electrons. All right. Both of them involve 1 plus formal charge and 1 negative. So there's no difference in the amount of non-zero formal charges. Then I think of my third rule. Remember, my third rule tells me that positive formal charges are going to be more stable on a less electronegative atom. Negative formal charges will be more stable on a more electronegative atom. So my electronegativity values I know that oxygen is greater than nitrogen. So if I have to choose, I would say this second set is more likely because my third rule tells me that negative charge is better on the more electronegative atom and the positive is better on nitrogen. So that tells me of these two possibilities, the second one is going to be more likely. All right. So as a first step into this realm of predicting reactions, that's actually a really using just some simple ideas that you already knew from modules 1 and 2, and this new idea of curved arrows, we can make a pretty decent prediction. Like I said, module 12 will give you more tools for evaluating this kind of reaction. But this is a really good first pass. So what I'd like you to do is try this example. So I'd like you to pause, try this example, see if you can come up with some different possibilities. And then after you've come up with at least one or two, I'd say at least 2 possibilities, come back and I will run through some of the possibilities that students have come up with before, and we'll think about which one is most likely. All right, hopefully you paused and took some time to come up with some possibilities. I'm going to walk you through my thought process here. So my thought process when I see these 2 molecules, first I'm going to think about partial charges. I notice that the molecule on the left is actually a negative ion. we have a negative formal charge on carbon, and then we have a nitrogen. So when I have, excuse me, that negative formal charge, since this molecule has a negative charge, both of these are going to be partially negative atoms. If you just go by electronegativity, you would say, well, nitrogen might be more partially negative, but that negative formal charge on carbon means it's also going to be partially negative. When I think about the other molecule, I know that oxygen has a very high electronegativity, so it's going to be partially negative. That's going to make carbon partially positive, and the hydrogens down here also partially positive. So now I can think of some different options. I could imagine that I could have attraction from the from the carbon with the negative formal charge to the hydrogen. I can imagine carbon with a negative formal charge over here to the carbon with a partial positive charge. I could imagine the oxygen. Well, the oxygen over here with a partial negative charge. It would be unlikely for that to go out and share with something that's already a negative ion. But I could also imagine the nitrogen donating electrons to one of the hydrogens, or I can imagine the nitrogen donating electrons to the partially positive carbon. So there's a bunch of possibilities. Let me explore some of those. So first off, I said I could have the carbon right here share with a hydrogen. If carbon's going to share with a hydrogen, I'm going to need to break a bond to make space. And so I could push electrons onto that other carbon. That would give me this set of products. And now this carbon's going to have a negative formal charge. I also said I could have carbon donate to carbon. Now, that when I share electrons with this carbon, there's actually two possibilities for the bond I could break to make space. I could break a bond to hydrogen to make space, or I could break one of the bonds to oxygen to make space. Let's consider those two possibilities independently. Let's break a bond to hydrogen first, see what that gives me. Now I'm going to have hydrogen with a lone pair. That's going to have a negative formal charge. I could also consider one thing I forgot to say. Our language sounds very aggressive when we talk about using curved arrows this way. We talk about a lone pair attacking another atom. So we'll say this carbon lone pair is attacking the partially positive carbon. So if I use that terminology, that's what I mean. Attacking really means sharing a lone pair with, which might sound a little off until you get used to that language. So I'm going to have the carbon lone pair attack the other carbon, but in this case, I'm going to break one of these of the double bond, one of the two bonds, the pi bond, to make space. And now consider what that gives me. Carbon is still bonded to two hydrogens now, and it's got a single bond to the oxygen, which will now have three lone pairs and a negative formal charge. All right, so that's so far I've considered the pink and the blue possibility. You might have also said, well, nitrogen is going to be partially negative, so maybe I'll have the nitrogen attack the hydrogen. If I do that, I need to break a bond to make space. So what'll that give me now? That gives me this product. Nitrogen now has a positive formal charge. Or you might have tried what I highlighted in green here, nitrogen donating to the carbon or nitrogen attacking the carbon. So I could have the nitrogen lone pair attack the carbon. And again, I have the two possibilities. I could break the carbon hydrogen bond to make space. Or I'm just going to flip this around to make it easier. Or I could break one of the carbon oxygen bonds to make space. Oh, and I meant to do these arrows in green just to be consistent with the color I used earlier. All right, so here is my fourth possibility. And you may not have generated all these possibilities. You might already be thinking, wait, some of these seem really unlikely. So really, we just came up with 6 possibilities. And that might feel daunting to you. You might say, well, how am I ever going to do this? Well, as you get used to it, you start to see patterns and you start to be able to make some predictions even before you draw out the products. But given that we've drawn out these products, let's evaluate them. So first of all of them follow the octet rule. So that's not going to be a distinguishing factor. But our first rule is follow the octet rule. They all do that. Second is minimize formal charge. So this whole second page where I use the nitrogen lone pair to donate, I'm going to reject all of those because all of these have 3 formal charges. In the products, whereas my first set of possibilities, all of these only have 1 formal charge. In the products. So these are all less likely. So I'm rejecting those. When this cyanide ion, this Cn minus, takes part in a reaction, it's almost always going to be the carbon lone pair that donates, or the carbon lone pair that goes out and attacks something. And the reason is, we want to have we want to have products that minimize formal charge. So I'm going to reject those. So now I'm going to compare these 3, which all have 1 negative formal charge. So I think now to my third rule, which is negative formal charges prefer to be on more electronegative atoms. And when I think about electronegativity, hydrogen is less than carbon, which is less than oxygen. So of these possibilities, I could have a negative formal charge on carbon, hydrogen, or oxygen. I would prefer to have it on oxygen. So my most likely scenario is going to be this one. And indeed, this is a reaction that you would learn usually toward the end of a first semester, or at the beginning of a second semester of a college organic chemistry class. Um, this is called part of the reaction called cyanohydrin formation. Um, so you have the tools in your toolkit to start to make these predictions. Now, if you came up with some other possibility that I didn't consider here, come and ask me about it. I have seen students try to get a little fancier with this. Um, I would I would tell you to shy away from trying anything fancier than this. Um, I could imagine maybe someone trying to take the oxygen lone pair here. That's partially negative, and maybe use it to attack the carbon. Um, if you did something like this, what you'll find is your formal charges in your product would be ugly. You would end up with a positive here, a negative on carbon, and a negative on nitrogen. Um, so if you came up with a possibility like that, it would be pretty easy to reject it, because you have three formal charges. You have negative on carbon, negative on nitrogen next to each other. Having the same charge next to each other generally is not a good thing, because like charges repel. Um, because this would be a very unstable product. So you may have come up with another possibility like that I didn't consider, um, but hopefully, using the tools you have, you would rule it out. Um, so yeah, pretty simple tools, and you now have a way to look at two reactants, and predict how they might react. Let me know what questions you have.